Swayam Prabha. Digital India. Educated India.
Very broad assumptions, they're not assumptions about particular things, but not saying something like factoring is hard, that's just one possible candidate, but we need some candidates like that. Okay, so once you have computational hardness, you can start kind of doing magic, in the sense that things that are not possible, that are not really there, but you can kind of have the illusion of them being there. And the first one I want to look at, and this is pretty much all we need for symmetric key cryptography, is compressing a random string. Okay? So in an information theoretic sense, you cannot compress a random string. I cannot use 4-bit strings to represent 8-bit strings so that you can decode them without error. Okay? So a truly random string cannot be compressed. However, if you're talking about computational bounds, you could work with pseudo-random strings, strings which are not truly random, strings that can be compressed but still look random. Okay? And that notion is a pseudo-random, pseudo-random number generator, or a pseudo-random generator, or a pseudo-randomness generator, if you will. So it's something which can generate these bit strings that look random to a computationally bounded adversary, but actually are not, they come from a small set. They can be compressed. They have a short description. Okay? And that's what a pseudo-random generator is. Okay, so you want to take a short seed. The seed itself will be random. Okay, say 1 to 8 bits or something, and from that you generate this long string, megabytes long or gigabytes long. And they will look uniformly random, like a uniformly random gigabyte string to a computationally bounded player. We'll shortly define what it means to look, but that's the idea. Okay, so you need to define it, right? It seems like a kind of vague notion that it looks random, and but it can be done. And in the late 70s, early 80s. People like Manuel Blum, Andy Yao, who are cryptographers / complexity theorists, and also Turing Award winners, incidentally, came up with these formal definitions, right? And we'll see one today. Okay, so what is a PRG? So here's the definition going to be. I'm going to drop a lot of the formalism, that is really needed to make sense of these definitions. I'll just put things under quotes and not get into the formalism, but it should give you the idea. Okay, so PRG, so that's how I'm going to call it from now on, is an efficient algorithm. Okay, so efficient should have been in quotes in the sense that it's something as part of your encryption, decryption, so forth, you'll be running this algorithm. So it has to work efficiently. And what does it do? It takes a k-bit string and outputs an n-bit string. It's a deterministic algorithm. It's not a randomized algorithm. Okay, so and k is short, so k-bits, short string, short seed, and you expand it into n bits. But what is random looking? Expanding is okay. It takes k bits, outputs n bits. But what does it mean for those n bits to look random? Let me give you 2 definitions, and then we'll see which one is more reasonable. So here's one definition. Okay, it's called next bit unpredictability, which means if you're a computationally bounded adversary, so everything is against a computationally bounded adversary. So there's quotes around. I call it feasible adversary. Okay, so we'll not worry about formalizing that. For those who are interested, it would be what would be called a probabilistic polynomial time adversary. Okay? So the polynomial time adversary. If you give it I minus 1 bit, so you generate this n bits from the, you take a k-bit string uniformly at random, pass it through this algorithm, get an n-bit string, give the first I minus 1 bits to this adversary and ask it, what is ith bit, the next bit? Okay? And it should not be able to predict it. Well, predict, clearly again it's kind of that question of, it's just a bit, you can predict it with probability half exactly, right? Well, if the next bit is going to be random, that's what's going to happen, right? Whatever you say, it's only exactly with probability half you will be right. Because with probability half, I'll pick your bit, with probability half I'll pick the other bit. That's what it means to be a bit being random. And we want essentially that to happen. Something very close to half should be a probability of getting it right. So let me just spell out the experiment. So a lot of these security definitions, this is the first one we are seeing today, are in terms of little experiments. Experiments are, I'll just show you what it looks like, and then at the end of it there will be some quantity that you will define. It's kind of the adversary's winning probability or advantage, and then the whole security will be saying, oh, no feasible adversary should have a big advantage. Okay, it's advantage. So let's see what the experiment for next bit unpredictability is. So there are actually many experiments. There is a bit I here that I mentioned. We want every bit to be unpredictable, right? For every I in 1 to n, every next bit to be unpredictable, including the first bit, right? That's also like next bit after an empty prefix. And we want this unpredictability to hold against every feasible adversary. Okay, so I'm going to define this experiment given a particular adversary and given a particular I that the adversary is trying to predict. So we draw a seed uniformly at random, generate R as G of S, so this is the output of PRG, and then give the first I minus 1 bits to the adversary. The adversary, so it's just a computation. It has to finish in some finite time to be feasible, to be called feasible, and it has to run in some limited time. Limit could be very large, but some limited time. I say that it has to output a bit. What if the adversary refuses to output a bit? You would say, if you refuse to output a bit, I'll take it as 0. Right? So you might as well output a bit. So without loss of generality, the adversary outputs a bit B. And the advantage of the adversary is probability that the prediction, so the bit B is supposed to be the prediction of Ri, so probability that the prediction was correct minus half. And I put an absolute value there because, if the adversary is getting it wrong all the time, that's also a good adversary, then you can flip the bit and find another good adversary, right? So I might as well put an absolute value. It's okay to drop that also. Okay, so this is the advantage of the adversary. Probability of the prediction being right minus half. Half stands for the probability of prediction being right if it was a truly random string, right? So you shouldn't do much better than or the advantage is how much better you do than when you are given a truly random string. So is the whole experiment clear? Okay, and to be secure, to be called secure, we say that the advantage should be very small, or the technical term is negligible. Again, I'm not going to formally define it. The advantage should be negligible for every feasible adversary A, okay, for every position I. That's the entire definition of a PRG according to this definition. Any questions on this definition? Okay. All right, so it's a reasonable looking definition, but why next bit unpredictability? Why this order 1 to n? What if I give you all bits other than the 10th bit and ask you to predict the 10th bit? Maybe that gives you an advantage. Right? Maybe that's what you can do. You need to look at all bits other than the 10th bit and then you can predict the 10th bit. That also is something, that's also a legitimate attack. Right? That will also say this is not a pseudo-random string. It doesn't look random enough. So, maybe we should change our definition. Sorry, just a minute. Yeah, change our definition a little bit. Here is a kind of a more correct definition or a more reasonable definition. It says, forget all this, whether it's trying to predict a bit or whatever. The goal of the adversary is to differentiate or distinguish between an input that is drawn from the truly random an input that's truly random versus an input that is coming from this distribution. What is this distribution? This is my shorthand for writing that experiment. You pick a random, uniformly random S, pass it through G. The output is an n-bit string. There's a particular distribution for that n-bit string, right? So you're sampling from that distribution. Okay? And the adversary's job is to tell you, it's trying to tell you whether the input came from this or that. Okay? So again, let's formally write down the experiment for this definition. So we flip a coin to decide whether we are going to draw a sample from this or this, truly random or pseudo-random. So we flip a coin, not showing the adversary. If the bit is 0, we draw a truly random string. If the bit is 1, we generate a pseudo-random string according to the right distribution of the pseudo-random string, meaning I pick a uniformly random seed and then I run it through the generator. Okay? And then we give the string to the adversary. So the adversary just gets an n-bit string, whether c equal to 0 or c equal to 1. And it has to output a bit trying to guess, it's basically trying to guess the C. It's trying to tell us, whether the string it got is from the pseudo-random distribution or the random distribution. Okay? It doesn't have to get it always right. Its advantage is, again, so if it was just guessing a random bit, since the C is, or guessing anything rather, if the C is uniformly random, it has a probability half of getting it right? If it always outputs 0 or always outputs 1 or picks a uniformly random bit, in all those cases the adversary has an advantage, or rather not advantage, it has a probability of B equal to C being half. Advantage is if it does better than that. Okay? So this half is something it would have even if our PRG was replaced by a uniformly random string, right? Without looking at this R, you can get this B equal to C to happen with probability half. So advantage is the extra probability of getting B equal to C. And again, we want it to be very small. Okay. So which of these two definitions do you prefer? This one, right? This one looks much more reasonable. It doesn't have any of these ad hoc quirks like 1 to I minus 1 will be given predict I. This is exactly what we want to say. This is what pseudo-randomness. This is what I've been implying all along, that it looks good. You cannot, no matter what you're trying to do with this pseudo-random string, it would look the same as what you'd have done when it was a truly random string. Okay. So this is the definition, except thankfully the two definitions are equivalent. And there's a little bit of a magical argument to be done. It's called the hybrid argument, to show that the seemingly weaker definition actually implies a stronger definition. Okay? And why do we care? The seemingly weaker definition is something easier to work with. When you want to show that there is no adversary here, you had to, it's this adversary which is trying to do a distinguishing. Here it's an adversary which is trying to predict the ith bit. You can work one bit at a time. You can say for each I, here is my argument why your ith bit cannot be predicted. So this is, we'll see actually a quick example of this later today. So this next bit unpredictability is a simpler definition to work with, and magically these two definitions are equivalent. There is some loss in the advantage, right? I said the very small advantage in this experiment, very small advantage in that experiment. They're not at the same scale. There's a kind of factor n difference. But as long as they're very small, it doesn't matter. They have to be really, really small. Okay? I'm not defining what very small means, but so with the proper definition of very small, these two definitions are equivalent. Okay, make sense? All right, so one thing to kind of mention at this point is that we already kind of said, right, truly random strings are incompressible, so we cannot hope to have a PRG that works against unbounded adversaries. So an infeasible computation can always break a PRG. Okay? So In particular, there is a brute force adversary which can get a significant advantage, can get a large advantage. So here's a brute force adversary. It's something you could have worked out, but since we're short on time, I'm just going to tell you what it is. So it's simple. It just takes an input R and checks, and this is the part where it's computationally unbounded. It checks if there is any seed S which could have generated this R. And if it is, then it'll output 1, otherwise it'll output 0. Okay, that's all this brute force adversary does. It checks if the input it got is in the image of the PRG. Okay, is it something that the PRG could have produced as an output? Why is this adversary? Why does this adversary have, why does it break this definition of distinguishability? Okay, so I'm using this definition right now, not the next bit in predictability. I'm using the distinguishing advantage definition. Okay, so let's compute what's the advantage of this adversary, since we have fully spelled it out. So let's compute all these things. Suppose C equals 1, so given C equal to 1, so conditioned on C equal to 1, what's the probability that A star outputs 1? Okay, well, when C equal to 1, we said we are taking an output from this pseudo-random distribution. So it'll always find some seed that explains the string. Right? So and it'll output 1 always. So this is probability is 1. The probability that A star outputs 1 when you are actually sampling from the pseudo-random distribution is 1. Let's also compute the same thing, probability that A star outputs 1 when the input is truly random. Well, so it'll output 1. So there are many, when you're picking a truly random string, there are 2 to the n of them. Some of them have pre-images. Okay? How many of them? Well, that's called the size of the image. But the size of the image of this PRG, those, if your R falls in or comes from that subset, then it'll output 1. So, of the 2 to the n possible strings R, the size of this image, that's the subset on which it will output 1. So this fraction is the probability. Okay, so this, and what is the size of this image G? What is G? It's a deterministic function, takes one of 2 to the k possible inputs. It takes a k bit string as an input. So there are 2 to the k inputs. Each input it maps to a unique output. So there can be at most 2 to the k different outputs. Could be less if some of the inputs lead to the same output, right? Then the outputs would be less in number, the image will be smaller, but in any case the image is at most of size 2 to the k. And n is greater than k, right? It's, of course, if we didn't ask you to expand the seed, then there is a truly, then there is a PRG, you just output the seed itself as the input. That's not really pseudo-random, it's truly random output. But when it is a PRG, that when you are expanding the seed, then this 2 to the k by 2 to the n is at least half, right? 1 over 2 to the n minus k. So it's 1 over at least, sorry, it's at most half. I'm looking at the probability that A star outputs 1. Okay, so it's a very small fraction which, where it will output 1. So most of the points, at least half of this fraction, half of the set, is where it's going to output 0. Yeah, you had a question?
So is the adversary trying to essentially recreate the entire key space that the PRG is? So PRG has a key space.
Or seed, I'm calling it a seed. The seed.
Okay. So if the PRG can create, let's say, 2 to the k power of keys, and the adversary is trying to generate a similar number of keys so that at least one can match, is that?
So the brute force adversary, when I wrote that it checks if there exists an S such that R equal to GS, yeah, you could imagine what it's doing is it's creating this huge table, going through all 2 to the k possible S's, checking if any of them matches, any of them gives R as the output from G, right? So it is, that's what brute force adversary is. It is going through all of them. Okay? And so it's only a small, and this gets, if n is much larger than k, this probability that A star outputs 1 when it's pseudo-random shrinks, right? If n is 2k, for instance, then 2 to the k divided by 2 to the 2k is 1 over 2 to the k. So, think of k as something big, 128 bits. So this is a tiny fraction. Right? So the probability A star outputs 1 when c equal to 0 is very small. Even if you're just thinking of expanding by 1 bit, it is small enough. It is less than half, less than or equal to half. Okay? And now that's not quite matching the definition we had. The definition said, what's the probability that A star's output is equal to C? Well, you can see, convince yourself that most of when C equals 1, it outputs 1. When C equal to 0, it outputs 0 most of the time, right? 0 at least half the time. So its probability of getting it right is at least 3/4, and there's nowhere near half. It's not negligibly far from half, right? So this is not a PRG. So of course the catch is that, so kind of the takeaway from that is that you cannot fight against computationally unbounded play. You cannot create entropy using a deterministic computation. Okay. So the pseudo-random string only has entropy at most k bits. It took a k bit string. If you feed it a uniformly random k bit string and look at the output has at most entropy k bits. So you cannot really fight against this brute force adversary. Our goal is to make sure that, not just this brute force adversary, any adversary, who manages to break this remains an infeasible adversary. Okay? So we want to make sure, in particular, the brute force adversary remains infeasible. Well, the k cannot be too short. If the k is too short, then this is not infeasible to go over all seeds, go over all 2 to the k seeds, right? If k is 8 bits and you go over all 2 to the 8 possible inputs, that's something you can do quickly. Even if k is 30 or something, you go over all 2 to the 30 things, which is like a billion, you can quickly go through that. So at that key length, you don't have a PRG. To make it a PRG, you go to something big, 128, or at least say 80 or something. But that's only protecting against this particular adversary, the brute force adversary, by picking, say, k equal to 60 or 80. You might be happy with the brute force security against brute force adversary. But what we are really worried about is all the other adversaries also. Something, some clever adversary that knows how our G works. That looks, and so we need to evade all of them. And that's where we need computational hardness. It should be computationally hard. There shouldn't be some clever algorithm that can do some check like this or any distinguishing test. Okay, so we'll come back to this at the end of the day today, if we have time really, to see how you could take computationally hard problems and turn them into PRGs. For now, we'll just assume that we have a PRG, okay, and see what more we can do with a PRG. So first thing we can do with the PRG is increase the stretch. So stretches, so you took a k-bit string and you output an n-bit string. This n minus k is a stretch, okay, and even if you have, so here I'm calling it t is a stretch, and even if you have t equal to 1, a PRG that just gets you one more bit, right? You can actually put that to use and get any number of bits. And how does that work? And here is the construction. It's something you would think of. So I've written this PRG as something that takes k bits and outputs k plus t bits. I've marked off some k of those bits, the first k, let's say, separately, and then the remaining t is coming down. And the PRG with a longer output looks like this. You just save the k bits that came out of this, don't produce them as outputs, use them as a seed again for the same PRG. Okay, and each time you do this, you keep getting T bits coming out. And you can do this any number of times, any feasible number of times, and the security definition of very small is such that this will still, so it needs a proof that this will still remain a secure PRG. If you started with a T stretch PRG, you can get an arbitrary stretch PRG. Okay? And at the very end, if you're done with your, you can output this seed itself. And so this, all these things outside this green box can be the output of this PRG. Okay? Of course, you don't need to output this last thing. You can keep it, just in case you need more bits to give out, pseudo-random bits to give out. And that object has a name that you might have heard of. That's a stream cipher. Okay? So a stream cipher is nothing but a PRG which can keep producing pseudo-random bits on demand. Okay? So how many of you have heard of stream ciphers before? Okay? Many of you have? Okay? So if you have not, that's also fine. This is what it is, right? We are defining what a stream cipher is. Now, the word cipher is a little misleading. It sounds like it's an encryption algorithm. It's not. This is what it is. It produces pseudo-random strings. Okay. So now that we have the stream cipher, we still need to do encryption. How do we do encryption? So here is a one-time encryption. So let me see. Okay. Here's how you do it with the stream cipher. So the key is going to be the seed for the stream cipher that Alice and Bob have shared. That's going to be used as a seed. And the way we are going to use the stream cipher is essentially use it as a one-time pad. Except the pad is now going to come out from the stream cipher rather than a truly random string. So it'll be a pseudo-random pad, not a truly random pad. Okay, so this is what it looks like. The message can come in, and it can come in as for now, the message can come in, and that's a thing here, and you generate a pseudo-random pad. You XOR it with, use it just like a random pad in as a one-time pad, right? And that's what the encryption algorithm is. The decryption is symmetric, just like we did for one-time pad, except now, your key needs to be passed through the stream cipher to generate the pseudo-random pad. So it's the same algorithm. And then, you just take the ciphertext as input, and then you get the message as output. With the same, as long as you're using the same key. And since, since the stream cipher can spit out bits on demand, you can actually have a stream here. Let me see. Yeah, you can have a stream of, the input doesn't have to be, you don't have to be told ahead of time how big the input is. You can start encrypting as soon as the bits start streaming in. Okay, so that's the stream cipher. Is it secure? Well, intuitively it should be. If no adversary can tell the difference between uniform random string and the pseudo-random string, it shouldn't make any difference whether you encrypt with this or that. If somebody could tell the difference between encrypting with this and that, they're actually breaking the pseudo-randomness, right? So the only catch is we are not defined security. We have defined security we defined perfect secrecy without any notion of, I said the ciphertext distribution should be the same no matter what the message is. That is not true here, right? Because it's only pseudo, perfect. So we need to define that security. We'll do that in the next lecture, but intuitively it should work, right? We'll see that next. Okay, to recap, actually, let's see. I have 15 minutes. I'm actually kind of halfway through the lecture, but we'll continue in the next one. So this is where we are. One-time pad gives perfect secrecy. Unfortunately, it limits a priori how much you can communicate. Stream cipher is a solution to that. You can expand your short key into a long pseudo-random pad. but it comes with its own limitations. In particular, the sender and the receiver, they need to stay in sync. So if it is a stream, it's probably okay, but if I had multiple messages to send you, and these messages came out of order at your end, then you'll have a problem. This guy, the receiver, Bob, will need to know which, it can generate this very long pseudo-random pad. It needs to know which segment of the pseudo-random pad has to be applied to which segment of the ciphertext or which ciphertext. So it's a bit of a hassle. You need to stay in sync, and you need to maintain state. The sender needs to maintain state. So sender, if you think of this key as something fixed, now it's not really, right? You kind of need to, if you remember how the stream cipher worked, at any point, the one example, the construction we looked at for increasing the stretch, at any point you have an updated seed, right? And you start from there. So it has to keep maintaining a state. So all sorts of inconveniences, and the fix for that is going to be to use something called a pseudo-random function instead of a pseudo-random generator. Okay, so let me go on and tell you what a pseudo-random function is. Or a PRF. Essentially, it's also compressing a long pseudo-random, long random-looking string into a short seed. Except now this random-looking string is exponentially long. What do I mean by exponentially long? Earlier you took this k, expanded into n. N is something still you're thinking of as your message length, right? So think of that as some polynomially long thing. But now we are going to expand it to something like, say, 2 to the k. Okay, and this is something, k is 128, 2 to the k is 2 to the 128. You don't have enough atoms in the known universe, or at least on Earth, maybe to store all of this information. So 2 to the 128 is a really, really long string. Okay, so we are never going to actually explicitly write down the string. But essentially that's what PRF is. It's an implicit representation of this 2 to the 128-bit string, which looks truly random to you, but it's actually explained by a 128-bit string or something similar. Okay, and then, so it represents this in what sense? It allows you random access. You can go and ask, I want the 5,000th bit of this big string. It can give you that. Okay, you can access that. You can give a number, an index into the string, and it'll give you the bit, or maybe a block, a bunch of bits at that position. Okay. So the function actually looks like this now. It has a seed as before, or key if you want to call it that. I will interchangeably use, at some point I'll start talking about these being keys. So it has a seed or key, and it also takes as input an index, I. And then it'll output, let me call it a block. It'll output not just one bit, it'll output the ith block of the pseudo-random string. So you think of the pseudo-random string as being split into 128-bit blocks, or some block length. And you ask it for the 5,000th block, it'll give you the 5,000th block. But yeah, there are exponentially many of these blocks, 2 to the 128 blocks. Well, that depends on how many bits you have to represent this I. So I is a 128-bit string, then there are 2 to the 128 possible values for I. For each one, it will give you a block. Right? So that's the number of blocks it has. Okay, so this is called a pseudo-random function. Well, that's kind of the syntax of it. The security definition is that it should look random. So we need to now define it. Same definition as before doesn't work. That was used to define pseudo-randomness of a string. Now we need pseudo-randomness of a function. Okay, so let me give you the definition. This is what the experiment is now. I have some pictures for the experiment this time. I have a multiplexer here, which is basically flipping a bit and choosing whether to, well, I'll show you the bit in a second. This multiplexer takes a bit as a control bit and decides to channel communication with this green thing here or this blue thing here. What are they? The green thing here is our pseudo-random function with a particular seed built in. That seed is chosen at the beginning of the experiment uniformly at random. Once, and it's fixed inside that green thing. This R is a huge object. It is this, a truly random string, truly random function. Okay, it can be implemented kind of efficiently when you get an input. You kind of check if you have answered already. If you have answered this query already, if you answered this query already, give the old answer. Otherwise, pick a fresh uniformly random string. Okay, so that's what this R does. You think of it as a computer sitting there and doing this. When it gets a query, it checks if that query is already answered, then it sends the old answer. Otherwise, it picks a uniformly random string, sends it, and records the fact that it sent it. What the adversary can, what we are going to do is pick a uniformly random bit as a control bit for this multiplexer, which just means, this communication is now going to be, so the adversary is allowed to communicate through this mux. It doesn't know who it's going to communicate with. That depends on this bit B. Okay? And this bit B is also drawn only once. And at the end of this, the adversary can, so it's a two-way arrow here, the adversary can make queries, get answers, make queries, get answers, any number of times. And at the end, it's trying to guess if it was talking to the pseudo-random function or the truly random function. Okay? Just to give you a sense of kind of how magical this PRF is, there are only 2 to the k possible seeds. And earlier when we were talking about PRG, we said, look, there are only 2 to the k possible seeds, and therefore there are only 2 to the k possible strings. And they have to look like coming out of 2 to the n possible strings, right? That was a PRG's output length. Here, there are 2 to the k possible seeds, so there are 2 to the k possible different functions. Choosing one of them should look like we are choosing a random function. How many functions are there? These are functions with the same, signature. They take, well, or rather, not same here. They take m bit inputs and output n bit strings. If you write a truth table for this, right, there are m bit inputs, so there are 2 to the m possible inputs. And for each input, there are n possible bits, n bits as output. So this truth table size is 2 to the m times n. And each bit can be filled in 2 ways in this truth table. So there are 2 to the power n times 2 to the m functions, from which r is coming. So it's a doubly exponential space. Okay. So earlier itself it was kind of exponential blow up, right? From say n was 2k, then from 2 to the k it was becoming 2 to the 2k. So it's polynomial, but it's a factor that's 2 to the k that's multiplying it. But here the number of functions is doubly exponential. Think of n, m, all of them as k, if you want. Well, yeah, this n is not the same as, this n can be shorter. This is the output block length. Even if it's 1 bit, this is still doing something. So think of n as 1 bit if you want. It's then 2 to the m, right? So it's really huge. It's pretending, this little PRF, is pretending to be coming from this very huge universe of random functions. Okay. So it's in another way, it stretches k bits to n times 2 to the m bits. It's doing an exponential stretching. Okay. Now, a PRF, we'll see this later, can be constructed from any PRG, okay, in principle. So we'll see that construction. That's not a very fast construction, but by the way, this R here is now the size of R. R refers to the input to this PRF, the I, the index I, what I was calling I, now I'm calling R. So the size of this I is what is called M in the previous slide. Okay, so it's a little, you can convert a PRG into a PRF, which is kind of magical, right? PRF looks like such a bigger object than PRG, but you can turn one into the other. That's not what's used in practice though, because you use fast heuristic constructions. And in fact, Again, if you've heard of stream cipher, you might have also heard of block cipher. Block cipher is essentially giving us this PRF facility. Okay? Now, for historical reason, a block cipher was never formally defined in the 70s or whenever people started using them. And it comes with a few other extra features that we really don't need for most of the applications of PRF, but it comes with it. So here's a syntax of a block cipher, right? It has a key built in, you could say, and also takes an input, an index, or this R. Sometimes it will show up as a nonce, a string, right, a bit string as input, and it produces an output. So think of everything as a block for convenience. So it takes 2 blocks as input, produces a block as output. But the extra features that it comes with, first of all, it's a permutation. It's a pseudo-random permutation. So what's a permutation? First of all, it takes 1 block as R and produces 1 block as output. And it's a 1-to-1 mapping. For every possible choice of the key, it's a 1-to-1 mapping from the input R to the output block. Okay. Further, it's not just it's a 1-to-1 mapping, it can be efficiently inverted if you know the key. Okay, it's another feature that just comes with block ciphers. And then, once you have this feature, and if people use that feature, it becomes a little, you have to assume that even with that access to this inversion, it remains pseudo-random. So it's a feature that's best not used in some sense. But the block cipher in the security literature comes with this feature. Okay. So any question on block ciphers? So I could stop here and we can continue after the break, after lunch. But I could take a few questions before we do that. Because as I was saying, that's still kind of only halfway through, or not halfway, but I didn't quite finish what I was planning for this session. Any quick questions before we? Yeah.
Sir, in the one-time part that you said that the keys need to be sent ahead of time. So, is there any kind of synchronization for the keys and the message? What if the keys are misplaced or something like that?
Okay, in one-time pad, I said magically somehow this key is already sitting with Alice and Bob. I'm not talking about how it's being sent. And further, being a one-time pad, there is no question of using it many times, so no synchronization issue. In stream cipher, I mentioned there is a synchronization issue. That the same stream, the long stream is being used to stream coming out of the stream cipher, the pad is being used to encrypt many pieces of the message, and the receiver has to receive them in those same order. You could instead say something like, I'll put an index as part of the message so that the receiver can compute it. But the receiver still needs to do maintain state. Suppose if you say, here is a message, here's a ciphertext. It was encrypted using the 100th, starting from the 100th position of the stream cipher. Well, then the receiver has to at that point run the stream cipher till that position and recover that. So it's just a bit of hassle, inefficiency. It has to maintain, or it has to maintain, So after, say, let me make it a little more dramatic. So first it was a million, position million, and then it was a position 100. Well, when you did this million, you'll have to store all this million, or you should be prepared to do recomputation, right? So it's just inefficiencies with using the stream cipher. Having said that, it's a legitimate. There are many settings where it is a stream that you're sending. In TCP/IP communication, for instance, you set up a channel, and they try to stay in sync, for instance. So it's reasonable to assume that, but not always. Any other question? Okay.
What if there are errors in the encryption, like in the transmission?
Yeah.
If errors are induced in the encryption?
Yeah. So we are not going to really talk about that here. You might have some thing in the. But the short answer is that error correction is something that will be done on top of this, right? So you take your encrypted message as a message to be sent through a noisy channel. use read solvent codes or whatever is needed for error correcting. So at the end, the receiver will get the ciphertext exactly as I sent. So throughout our lecture, we are not worried about communication errors. Yeah.
So considering the message masking for the stream ciphers, how will be done in pseudo-random function? The message masking.
Okay, you're asking how you would use a pseudo-random function to encrypt, right? I've not got to that. That's a couple of slides from here. So that's what we'll start with next time. Okay, so this is so far just a pseudo-random function. I said the purpose of this is to do encryption. It will help us with encryption, but I have not told you yet. Okay.
We got 2 power n into 2 power m. So how did we got that?
N times 2 power m, I think. What I was saying is that you should think of, so we are counting how many functions are there that take m bit inputs and give n bit outputs. What is a function? You can write it as a big table. For each row of the table is the n bit output it will give on the input. Input is an index into the rows of the table. How many rows does this table have? So it's m bit input, so there are 2 to the m rows. How many columns are there? N bits, because that's each row is n bits long. So this table is 2 to the m times n. And now how many such tables are there? Well, 2 to the power of that, because that many bits.